All right, everybody. Good morning to you guys. Hope you guys are doing well. See how things are going, so you know. All right, so we got a little bit late start. That's okay. Good morning, Paula. Lila, good morning to you. And Oscar, good morning to you guys. So anyway, ladies and gentlemen, let's see what's going on here. Let's go to the browser here. Right, and we want to scroll out. It's not for you guys here. That's a different class. I was looking at a few things this morning. Where are you at? No, we don't want to do that. Anyway, what is this? I'm not going to FaceTime anybody. All right, let's go here. Where are we at? We're going to go to the website. Sorry, we're going to go to Math 262 if we can get there. Calculus 2 worksheets and videos. Not there. I think we're going back over here. Online transition. Here we go. Where are we at? The improper integral section. Share with you guys. We're going to work with today infinite discontinuities. I'm sorry. Yeah, what they call infinite discontinuities anyway. What do we call it here, though? What did I call it in this worksheet, if I can get there? Let's scroll in. Now we're going to look at the second type, second class, whatever you want to say, however you want to describe it. Remember, typically, you have integrals that are thought of as proper. Remember, you got an integral from a to b, fx dx. This is a proper integral. In the sense, it's proper in the sense that, again, this function f, right? We're going to say this. F is continuous, right? Over a closed bounded interval AB. Let's make that look like an A. And this is what we've known. This is what you guys have been working with, right? You got this interval. And so now, just so you guys know here, now, when we talk about this type of integral, you're going to have a function now that's going to be discontinuous at some point in the interval, right? So you say, what are you talking about, right? So let's go back here. Let me copy this now. So what I'm going to remark about this here is this second class that we're going to deal with. See this function? Right? F is now this what? Continuous at some point C in the interval AB. So you got a discontinuous function now. Okay? So this is what we are working with today. So like, for example, just give you guys a quick kind of reference here. This is what we're talking about. You would have never seen a question like this before in your life up until today, right? So if you had something like this, 1 over x dx, right? So here's good morning. How you doing? So you would have never seen this before, right? And you say, why would we not see this? And maybe change this a little bit. I want to do a nicer picture. You would have not seen this in your life before because if you look at the graph, right, we consider this curve here. Let's see what's really happening. Right, as you integrate from -1 to 1, right? Here's what I want to show you in a very simple kind of picture here. What they're asking is, hey, what's the area under the curve here? And what I want you guys to emphasize, or I want to emphasize here, let's get the highlighter out. This is what I mean about it. 1 over x squared is discontinuous, right? At x equals 0. It's discontinuous at 0. All right, you guys with me on this one? It's 1 over x squared. So you would have never had that in Calculus 1 because Calculus 1, the requirement was that the function always had to be continuous. So they would have just changed the interval in Calculus 1, right? You guys know what I'm talking about? They would have put like from 1 to 3 or something, or -4 to -2, you know. They would have just changed the interval on you. But now Calculus 2 comes along and they say, okay, we have these things called improper integrals. This is another type of improper integral, right? So let's actually handle that. It's an improper integral. So in order to handle this is what I give you guys this morning here. We need a couple of definitions again. There's a couple of cases that we have to look at. So like for case 1, you know, really what you're going to start to look at is what we call a discontinuity at an endpoint. So that's how we're going to have to approach this. We start with a discontinuity at an endpoint. So even though they say, you know, this type, and then you have a case 1, I'll give you case 1 definition here. Right? If we read this, the function f is continuous now over the interval from a to b. And notice what I just did, what I wrote down right here. This is going to be the thing about this, right? We still have the integral from a to b. But this function is continuous over, take a look at this. This is an important detail. Okay? If you notice how that interval was written, this function is discontinuous at the endpoint. Okay? Right here is that discontinuity at x is b. So this b value, you have a discontinuity. It's just saying you're discontinuous at an endpoint. You have to start with these two cases. Really, you have to start with these two cases before you can answer this simple kind of question, ironically. Okay? So you have what's called a discontinuity at your right endpoint, right, from A to B. And a general picture, there's a lot of pictures people draw of this. And if I said to you, let me try to draw a picture of what I'm talking about. Right? You have an interval from A to B. But what's happening at B? You have a discontinuity. So I'm going to draw that same kind of picture. So it's kind of like saying, hey, we got this situation. Right? It's not discontinuous at A, it's only discontinuous at B. And then they're still going to kind of ask you, hey, can you actually find the area under that curve, right? But at last time, the curve got close to the x-axis fast enough so the area was finite. This time, your curve has to get close to the, what you call that axis here, right? The discontinuity at x is b here. Does it get close to this imaginary axis fast enough? Because you're going to have two situations. Either this area is going to be what? Finite, or it's going to be what? Infinite. Okay, when it's finite, we say that this actually what? Converges. Yes, when it's infinite, we say it diverges. So, I mean, this is kind of like what they want to describe as a right endpoint here, discontinuity at a right endpoint. And how you handle that is very similar to what we did yesterday. So let me go back and let me express to you what we're really kind of trying to do, right? What you're going to do is you're going to take that same integral, and you're going to define it this way. You're going to integrate, instead of from a to b, you integrate from a to t. Okay, so you're going to introduce another variable again. You're going to find that area. And that area I like to call, like I called the area before, this is I of t for me. So you say, okay, I'm going to find that area, integral in terms of t. So we're going to redefine this. Okay, so let me give you guys the definition here. It's really based on that picture. The integral from a to b now, f of x dx, is the limit now. So take a look. Take a look at what I wrote here for the definition. Is the limit, your t is going to go to b from the left side of the integral from a to t fx dx. So in my definition there, right, you say discontinuous at the right endpoint. This is what we're using here. Okay, it's discontinuous at b, the right endpoint. So this is the problematic endpoint. I'm going to highlight that. It's discontinuous, and we're going to introduce that dummy variable again. But notice this. We're going to now let this t go to b. Right in here, this t value is going to go to b from the left side. So it's on the left of that. So we're going to find that area in terms of t, and hopefully it converges. And if it does, we're in business. Right? So that's the definition we're going to have to use. So let me give you guys a quick example here. Some of these kind of questions that they're going to give us, like if I integrate from 0 to 3, and I have 1 over x, or actually, let me do something here. I want to change this question. What do I want to do? Oh, whatever. Let me make something up, okay? Always dangerous when you make it up. Well, I'm gonna do it this way. Let's look at that same one. Integral from 1 over x squared dx, but I'm going to look at it from -1 to what? To 0 dx. Okay? So you guys can see my point. So when you go back to that curve again, where is it discontinuous? I just changed this question on you guys. I'm looking at the left side here, right? So I'm looking at this here. -1 to 0. So my right endpoint, there's a discontinuous value there. So here's my problematic. This is where my x is discontinuous, right? So 1 over x squared, discontinuous at the right endpoint. Definition. We say, okay, integrate from what? This is going to be the limit now as t goes to 0 on the left. We're going to integrate from 0 to t 1 over x squared dx. Yes. Oh, I apologize. -1. Yeah, should be. Let's get that coffee in. Okay. And remember, this is the substitution right in here. Right? And remember, you're going to 0 from the left side, right? So you go back to that picture. I'm kind of saying, look at it this way, right? This is the t now. So you can go from -1 up to t, and then find that area in purple, and then let t go to 0 from the left side, because t is to the left of 0. Is that right? That's what the idea is. T is to the left of 0. So, okay. So, all right. So, as you guys know, you're going to have to integrate. So, that's x to the minus 2. There's 2 parts again. So, I'm going to use the same colors like last time. Gray. And then I'm going to use what? Gold. So, we got to find that integral here. So, this is going to be negative 1 over x evaluated from negative 1 to t. Is that true? All right, you guys okay with that integral? And use your limits now. So that's going to be negative 1 over t minus, be very careful with this stuff, ladies and gentlemen. Notice what I did here. That's big F of x. You know, I find it helpful sometimes to do what I'm showing you guys here. Because you got a bunch of negatives, you can like leave one off, you guys know, and it's kind of irritating. Right? So that's negative 1 over t minus a negative 1 over a negative 1. So, anyway. So you end up with what? 1 over t minus 1, I guess. Okay, you guys okay with that one? So what do you need to do with this limit now? T goes to 0 from the what? From the left now. Okay, double check we're doing the right arithmetic. We're okay with this one. And in order to do this particular question here, right, let me use properties of limits. Properties of limits, remember, limit t goes to 0 from the left, negative 1 over t minus that limit, t goes to 0 from the left, of 1. This is a constant, so this is going to be your 1. Now, what happens over here? You guys know? Where does that go to? Remember I started the course and said curves every calculus student should know? Huh? Well, what does this look like? Does it go to 0? This is t now. This is 1 over t. So to really look at the details here, right? This is what I'm saying. This is minus limit t goes to 0 from the what? Left of 1 over t. And this portion goes to what? Minus infinity. But this is minus a minus. The point I'm making is that's infinity. Okay, you guys okay with that one? So that limit is infinity. Is that true? And so what is infinity minus 1? Is that infinity, right? Remember, Oprah money and she spent $1 still means she has Oprah money, right? So what do we know about this particular integral? This one diverges. Good job. Diverges. Absolutely. Diverges. And so what does it really mean about the area? That area, right, it's uncountably large. In other words, let me get rid of the purple if I can. Hard to do. But what I'm saying here in this question here is this area is actually infinite. The curve doesn't get to the y-axis fast enough, so it's finite. And what that now means is if you said to me, okay, well, I mean, I haven't given you the other, the other definition yet, but we'll get there. But this left portion is going to be what? Infinity. And that's that. So you have a discontinuity at a left endpoint. And this is this particular integral. So you start off by focusing only on discontinuity at an endpoint. This is going to be, I think I said left. This is the right endpoint, right? The right endpoint discontinuity. So that's where you first start with the definition at one right endpoint. And then I can show you, well, how would you answer this question? Well, you need the definition at the left endpoint discontinuity. Haven't given you guys that one yet. I can give it to you if you guys like. It's not a problem. To compare and contrast, I'll give you the definition quick and fast. What if you have a right endpoint discontinuity? It's in the notes here. We call that case 2. Right? How did I write it? Where did I give you the there we go. Definition. Okay. So now if you have a situation where you have a to b, f of x dx. Let's say you have a discontinuity at a. It's really the left endpoint. Right? So f is discontinuous at x is a. That's the left endpoint. Okay? So now I can define it for you guys. You're going to integrate this. A to b fx dx. Replace that with a what? A t. Right? That's the limit of what? T goes to a now from the right. You're going to see what I'm talking about. So, for example, the integral from now 0 to 1 over x squared dx. So here's my situation here. I'm going to draw you guys another picture. This is the curve. And as you guys know, this interval now from 0 to 1, okay, you have a function, your function f, though, we have to remind people here that f is continuous everywhere else except on the left. So they'll put a to b. This means it does not include the endpoint a with the parentheses. So you have a continuous function except at an endpoint is really what they're saying. And in this case, it's going to be the a value. Okay, so this is kind of the idea. Now remember, they're going to say again, do this here. Don't integrate there. Integrate from t to 1. Find that area. Now t will have to go to 0 now from the right side. That variable t. You're going to go, remember, this is 0 and this is t. You're going to go from the right. This is my integral I of t that we've been watching. So you just apply the definition because the issue is at 0 here, right? So this will be the limit. T goes to 0 from the right. We're going to integrate from t to 1, x to the minus 2 dx. So again, negative 1 over x, t to 1, it can get a bit confusing. If I don't write this down, I might make a mistake. Here's my point, right? Here's my f of 1. Is that right? Minus 1 over t. So I have to write that down and think about it that way, ladies and gentlemen. So that's my advice to you guys. You're going to have like some negative, antiderivatives, and then you have some subtraction with some negative numbers. It could get a little tedious, and you got to be careful. This is how I'm careful with that, right? Negative 1 plus 1 over t, or 1 over t minus 1. So now you apply the limit, right? So this will be the limit. T goes to 0 from the right, 1 over t minus 1. So we've got to apply that limit now. Okay? And so what happens here now? What happens as you go to 0 from the right for 1 over t? Do you guys know? Let's go back to the curve of 1 over t. Yeah. Goes to infinity, is that right? Good job. So, I mean, I can say, isn't this going to be, again, infinity minus 1? I don't have to write down the properties, right? And then that's going to be what? Infinity? Now, that should make sense. Let me tell you guys why this makes sense. This area we found out is actually infinite, right? And isn't that like area above the x-axis? So it should be positive, right? Just kind of remind you guys. Just like up here, we did the other side. This is also infinite. It's above the x-axis. We did the left side. Okay, you guys okay with that? And so, ladies and gentlemen, they both are consistent. They don't get to the, vertical asymptote fast enough. X is 0, so the area explodes. It's uncountable, infinite. You can say this diverges, right? And so that's really the two definitions when you have these endpoint discontinuities. However, you might say, but Mr. Judge, what about the original question, right? What about how I started the day? We integrated from negative 1 to 1 over x squared dx. This does not have a discontinuity at an endpoint, right? This function is continuous. Well, let's rephrase that. Our function is continuous at the endpoints, but it is discontinuous where? Yeah, at 0, right? So it's discontinuous at x is 0. So you say, what? You started the day with this kind of question. I know. Well, here's what I'm going to say to you guys. You want to fix this, not by algebra. I'm going to say you can write this integral. Remember this here? Use the discontinuity. This is going to be the sum of what? From 0 to 1. Where's your discontinuity? 0. Guys, see what I'm saying? You split it up into two integrals. So the reason they have to talk about case 1 discontinuity at one endpoint, case 2 discontinuity at another endpoint, because generally speaking, if you ever have to integrate a function that's continuous everywhere but at some point in the interval, you have to split it up. And this is going to be, notice this is case what? 1, and what is this? Case 2. There you go. That's kind of, in some ways, ladies and gentlemen, that's the lecture for today. You know what I mean? So if you're going to find, but here's what I'm going to have to say. If you're going to get convergence, you got to get convergence for both. You go, what do you mean? What are you talking about? Yeah, let me give you guys a big note, right? This is just writing it arbitrarily. Integral from a to b, fx dx, where f is discontinuous. at a C in an interval AB. And it has only one discontinuity, right? So anyway, how do you write that integral, right? This integral will have to go from A to C, fx dx plus C to B, fx dx. Remember, the problem here is at some C, you have discontinuity. Now, if you're going to get convergence, right, the idea is convergence. If we want to say that this integral converges, area is finite. What do you have to have? You guys know what you have to have? You both have to converge. Absolutely. I'm just trying to figure out what colors. Yeah. Case 1, maybe. Case 2, you know what you have to have? You have to have convergence, and you have to have convergence. Does anybody know why? Why do you have to have convergence for both? Yeah, infinity plus any number will still be infinity. Or a number plus infinity isn't. Think of it like Oprah money. Is that right? If you gave Oprah $1, you know, she still has Oprah money. Is that right? You gave Bill Gates $1, still has Bill Gates money. So my point is, this is finite numbers. Finite plus finite is going to be a finite number. So you got to have convergence for both. If you don't have convergence for one, you want to know what that means? Stop right there. You don't even have to go further. You already know what diverges. You don't have to. That's it, done. So it's a kind of like ironic that, you know, if you're going to see about convergence, you know, that's the deal. Anyway. Well, I think it's kind of like looking at the homework. Let's see, how do they, you know, write it? I kind of try to stick with what the homework does. And I'm thinking of giving you guys an extra credit assignment so you guys know. Oh, did I? Oh, I gotta remember. See, yeah. See how old men are. Yeah, no, because you know what I'm doing is I'm giving some extra credit for like a statistics class due to that AB 1705 stuff, right? I normally don't give extra credit, but it's kind of a special semester in honor of this bill I've been working on or working against, right? Trying to provide students with choice so that they can, Trying to provide students with choice so that they can have opportunity. You know, they're trying to get rid of all the pre-transfer level math and English courses, right? Say, hey, you can't take that. We're just going to put you in a transfer level course, and they're going to tell you things like, hey, if you fail, just try it again. Oh, get some tutoring. Oh, take some concurrent courses at the same time or whatever, right? And that's easier said than done. So things like, because I remember, you know, I'll get into the details of the gory details of this stuff, is, you know, like if you said, I want to take a calculus course or maybe let's start before that. What's your really first transfer level course if it's in STEM? I believe it's like it's either college algebra, okay, depending on what the major is, or it's like Math 260, right? So in order to be successful in those classes, what do you guys need to know? Like algebra. You know what I mean? There's no way around it, you know. So you might say, what kind of algebra? Well, you need intermediate algebra. And I have like some students in my intermediate algebra who want to take college algebra or Math 260, and they're struggling with intermediate algebra. They really need a beginning algebra course, in all honesty. But, you know, the politicians, and there's a reason why politicians are doing this. Trust me, there's always reasons. They want to say, we're going to get rid of those courses. You would think you guys know what you're doing. So it sounds crazy because you go, why would you remove opportunity from people, right? Why would you ever do that? That goes against your community college mission, by the way. Well, in case you guys don't know, there are people who are sponsors of some things that want to get some people into for-profit situations where you borrow a hell of a lot of money. I'm going to not name a for-profit, but my younger brother, I'll give you guys a quick little story. My younger brother, a little personal family history here. My younger brother, you know how younger brothers are? Do younger brothers ever listen to older brothers? You guys know what I mean? Sometimes, right? Sometimes, personal story. Love my younger brother dearly, but younger brothers don't always listen. Wives don't always listen. Husbands don't always listen. People don't always listen. So people don't always listen. But anyway, make a long story short, he went to a for-profit. I told him not to. Wouldn't listen to me. So he ended up with a bachelor's degree and an MBA at a for-profit. You know how much money he owed when he left? $100,000. And nobody would hire him because they knew it was a for-profit degree. Heartbreaking, ladies and gentlemen. Heartbreaking. I don't want to give you any more of that personal family drama. Love my brother dearly, but he didn't listen. So, I just don't want other people to fall into that trap either. So I'll be speaking to our board, trying to get our board tomorrow on Wednesday at 1. And, they're going to want a 1 or 2 minute, presentation. I mean, not 1 or 2 minutes. You can't really talk to the board, if you guys want to know the truth. Hard to talk to the board. So say, okay, if you want to talk, you got to give us our name, give me the list, blah, blah, blah. And then you get 1 minute. You get 3 minutes. So it's a real thing, So anyway, trying to get our board to push back against it. I met with, what's called the liaison for the higher ed committee for the state of California last week. Had a meeting, giving them a presentation on all the work I've been giving on the data and information. So, hopefully they'll listen. But, politicians, what do they listen to the most? Whoever financially backs them. So it's an uphill battle, uphill fight. But hey, you know what? I don't know about you guys. This is a good, worthy fight. And I never back down from a good, worthy fight. I just don't. It's not in my DNA. You guys know? I just don't. It's just not going to happen. So it's a good, worthy fight. So I'm gonna give the good fight. And at the end of the day, I can sleep well at night knowing I gave a good fight. It's kind of how I see it. But anyway, why am I telling you guys this story? Oh, yeah. So my statistics class, I get to talk about the statistics behind this and teach them the statistics of what I'm using for the analysis because it's the course. So, I give them an extra credit if they want to speak, Speak against. I even say, you can even speak for it. I'm not going to tell you guys what to think or what to do, You have a right to determine for yourself. Just like I say, students have a right to determine where they want to take a pre-transfer level math course just to help themselves, in their academic pursuit. So I'm not going to, become what I condemn, trying to limit what you, can say or feel or believe. I may disagree, but that's another story. That's not the point. So if you guys want to just give me your name, I'll try to see if I can put your name in if you want to speak for a minute or two. Send me your name via Canvas, and then hopefully, let me check my email. Hopefully they don't limit. Oh, you should have got the names in a week before. You guys know what I mean? So this is how it works. I'm telling you. Really? Is this how our political system works? You know what I mean? Oh, you didn't give me the name a week before. Let me check my email. I'm telling you guys. Anyway. So I'm giving them that opportunity to speak. I'll give that to you guys too. So far, yeah. Oh. Yeah. And I did submit the information to the rep. Oh, look, she's actually thanking me. Thank you for providing this information. Alan says already Monroy. So I provided some stuff. It's crazy. You guys know it's really crazy. So I don't know. If you guys want to speak, let me know, and I could give you some extra credit points. I'm offering them like 20 points. So let me know ASAP. We'll try to get you in. But I also give you another extra credit assignment on like improper integrals, you know. So keep an eye out for that. So I apologize if I haven't got to it, but I mean, I've been working every week. I even had to work Easter. And my daughter's like, Dad, come on, it's Easter. It's like, sweetheart, you don't realize. So I'm going to tell you guys what I tell her. Say, Ashley, you do what you have to do, not what you want to do. And when there's a fight, I'm not going to take a break in the middle of a fight. You know, if I'm going to fight, I'm going to fight to win. Otherwise, I'm not going to fight. You guys know what I mean? You don't just get in. Trust me on this. This is some wisdom here. You don't just go fight for the sake of fighting. You just don't. That's crazy, you know. But if you're going to have to engage, you engage to win. That's it. You know, that's how I see it. So, yeah, I'm going to try to give the good fight. And at the end of the day, you know, we'll see where things land. And hopefully we make a difference. But, so, yeah, I even had an interview, all these meetings. You guys don't realize how crazy it's been. So I got the extra credit assignment for statistics. I got to get you guys a nice extra credit assignment too. So you have the opportunity to speak. Let me know as soon as possible because it's tomorrow at 1 via Zoom. It's tomorrow at 1 via Zoom. So let me know if you can make it. If not, it's okay too. But it's fun if you're doing the right thing. You know, it's not fun if you're not. So I'm engaged in every way you guys can believe, even on social media, because they have a campaign. They're very well funded. It's a whole campaign, ladies and gentlemen. This is real stuff. They think they're helping people, but they're not. You know what makes it suspicious? If you really want to help somebody, why would you want to remove choice? You see what I'm saying? Why would you want to remove choice? Doesn't pass the sniff test for me. If you really want to help somebody, you would say, hey, if you want to try it, go right ahead. Good luck to you. But if you don't find it successful or you think it's problematic, you still have a choice. That's what I think this is the better approach. But they don't want to do that. They want to remove all options for you. That's what makes it suspicious. What's the end game? You know what I mean? The end game is disenfranchisement and putting people in a desperate situation where now they can increase the market for what? These other options. And that's horrible. Never thought I'd see the day. But we're living in some crazy, interesting times. You know, I don't want to have to bring up world politics even, like what's going on right now in Ukraine. You know, that's horrible, horrible, horrible. I don't even want to go there because every day you read the newspaper or you watch the news, it's not a pretty picture. So anyway, never thought I'd live in this world. Glad I can focus on what? Improper integrals. This is why, ladies and gentlemen, in all honesty, this is why I loved and focused on math, because it made sense and because it was easier to solve than all these other problems. That's why I did it. It was the lone sanity in my life to everything that I was ever going through when I was younger. That this integral will have one answer only. And if it was wrong, it's because I made a mistake. I could go back and fix that mistake and find out. And take a look at this situation, right? So look at this function. They give you a closed interval from 0 to 3. Right? They give you that. Where is this function discontinuous? Because they're going to give you examples that are discontinuous. This is discontinuous where? Do you guys remember? Where is your denominator equal to 0? X is 0. Is that right? You have a vertical asymptote. You might as well just say, where do you have a vertical asymptote? You guys know what I mean? That's all they're asking. Where do you have a VA? The denominator is 0. You say, how do I know? Well, set that equal to 0 and solve for x. And in fact, if I do a little bit of algebra, isn't this x to the, this is x to the 1/2, which is x to the 3/2, right? So x to the 3/2 equals 0. That means x is 0. This is my point. So this is going to be what kind of situation? This is a left endpoint. Left endpoint. So maybe we should go back and label 2 definitions. This is my what? Left endpoint discontinuity. Right? It's a left endpoint. So you're going to approach the number from the right. Is that right? You didn't even have to graph this. You just approach it from the right. Limit t goes to 0 from the right. Integrate from t to 3. And this will be 1 over x to the now 3/2 dx. All right, so you might say, can I replace this with x to the minus 3/2? Right, we can. So I'm going to integrate here and here. All right, you guys okay with that one? And then you say, what does this give you now? Well, x to the minus 3/2 plus 1 over minus 3/2 plus 1. Remember that? And you evaluate that from t to 3. So what is this 1 going to be? Is that 2 over 2? Right? 2 over 2? So that's x to the minus 1/2 over a minus 1/2. Isn't that going to be? It's like minus 2 over the square root of x. Is that right? So like I said, it makes it easier if I say, oh, that's f of 3 minus f of 2. So it's minus 2 square root of 3 minus a minus 2 square root of t. And then minus and minus, this is you're going to get 2 square root of t minus 2/3. Okay, now you got to take the limit. T goes to 0 from the right. So properties of limits. Limit. T goes to 0 from the right. 2 square root of t minus that 2/3. So this is all based on what happens with this limit. Because 2/3 is a constant, right? Limit of a difference is difference of limits. Limit of a constant. So that constant is going to be the constant. Yes? Well, oh, yes, square root of 3. Thank you. You're right. Okay. However, what's going on with this limit? Do you guys know? T goes to 0. Do you guys know what's going on? You know what I'm going to say to you guys? Isn't t positive here, right? Because I do say to people, why don't you do something like this, right? Look at the curve. Well, this curve might be harder to consider. So you know what I'm going to do instead? I'm going to think of it numerically. T is going to 0 from the right. What if I tell you, what is What is close to 0 that's positive? Like 1 over what? Like 1,000 or something? You guys know what I mean? And when you put that number down in here, what do you think that does when you put a small number in the denominator? Then the fraction gets what? Bigger. And the smaller you get, the bigger it gets. You guys see what I'm saying? That's a pretty cool trick, I think. And so the reason you say, is that Oprah money minus whatever number that is? Yeah, and it's still Oprah money. Or Bill Gates money. By the way, Bill Gates is partly behind some of that stuff, these foundation stuff. It's infinity. So what do we say about this integral? Diverges. What do you guys think? Is that okay? Yeah. You'd have to break it up into two integrals. And what I'm going to say, those are usually at the end of the section. So they're going to start by giving you a whole bunch of left endpoints, a whole bunch of right endpoint discontinuities. And that's really what you want to focus on. The Sunday would be when they give you, hey, in general, you know. So I like to start the lecture off that way so that people can see the whole picture. But they're going to give you a whole bunch of left endpoints and right endpoints. You know, and then when they give you the discontinuity in the middle, then you go, oh, I got to do 2. And that's the kind of the deal. But, you know, the devil's in the details. Like, for example, if I said to you, let's give you another detailed kind of situation. The devil's in the details, meaning if they give you this kind of question, and I think some of these I've taken from like the book, in all honesty. And remember what you have to find. They say, they're going to give you, you're going to have to find, is this a left endpoint or a right endpoint discontinuity? You know. And so you might say, how do I find out, right? Well, remember what I was saying here? You're trying to find the vertical asymptote, right? So if you set this here, 1 minus x squared equal to 0, you want to find where that vertical asymptote is. What does that mean? When does this happen? That only happens where what's under the radical has to be equal to what? 0. Right? You guys okay with that? You guys with me on that one? And then this becomes a nice intermediate algebra question. In all honesty. You go, really? Yeah, I'm teaching this kind of stuff in the intermediate algebra course. So then x squared is 1. And what does x become? Plus or minus square root of 1. X is plus or minus 1. X is positive 1. X is negative 1. Now, what's the interval? The interval is from 0 to 1. What do you know about this situation? This does not imply. X is negative 1 is outside the interval. So where do you have your discontinuity, ladies and gentlemen? Don't you have it at 1? Okay. So this is discontinuous at 1. Is this a right endpoint or a left endpoint? That's a right endpoint discontinuity. So this is that, we called this one case 1 earlier today. Right? So my function is discontinuous at 1. So, I mean, that's the detail that you got to consider. So you go, oh, yeah, okay, discontinuous at 1. That was the first, that's a right endpoint discontinuity, right? There you go. Here's the right endpoint. So this is going to be, by definition, you're going to go to the discontinuity from the left, right? So you go, okay. So you're going to write down the definition now for this. This will be defined to be the limit. And now it's kind of like, oh, this is my discontinuity. T goes to 1 from the left, integrate 0 to t, 1 over square root 1 minus x squared dx. So I'm going to copy this here. All right. So emphasize that here. This is where the t is. This is the t. Okay? So then the question becomes, you guys recognize this anywhere? Inverse what? This is a special integral you guys want to know. It's inverse sine. Yeah, inverse sine. Mm-hmm. Inverse sine. Absolutely. Now, inverse sine is 0. Do you guys remember what that number is? Where is actually sine 0? I mean, I know it's like the same number, but if you guys remember how to evaluate that one, right? I think of it this way. Remember, this is actually answering sine theta equals 0. Your sine curve, that means theta is 0. 0 there. So you just simply have inverse sine of t now. But you have to take now the limit. T goes to 1 from the what? Yeah. Now remember, inverse sine, I believe, what do we do here? Do you guys remember the inverse sine curve? Should go to 1? Remember, you're going to try to deduce this stuff. And sine, if you guys remember, sine had to be 1 to 1. Is that true? Right? You had a restricted domain. This is where, like I said, the trig course comes in, blah, 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 blah. There you go, Mr. Judge. You're preaching. Yeah, I'm thinking that. Is that the 1 to 1 sine? Yeah. 1. Anyway, so I can go back. So in other words, this is for sine, ladies and gentlemen. That's not even inverse sine. But what's the point I'm trying to make? If you're going to go from 1 from the left, what is this limit going to be? Pi over what? 2. So you can kind of deduce the sketch. This is for sine. You can get now the sketch for inverse sine, right? And you'll find that that becomes pi over 2, which is finite. So this is the first time we get a nice convergent question. Okay? So notice it's just some fundamental trig to some degree there, right? Definitions of trying to get those inverse sine functions. There you go. So like I said, it's a little bit of the devil in the detail kind of remark. A little bit of that. And then I got to see, where does this question come from? Yeah, I don't know where this one is. I think it's this one. Okay. And then, just going to keep an eye on the time. And then, ladies and gentlemen, let's give you guys a nice good one. Not a good one. It's very similar. Like I told you, devil in the details. So you're going to integrate now here. 0 to 4. 1 over. Okay? Now, that interval is from 0 to 4. And remember, this function is going to be discontinuous or have vertical asymptotes where the denominator equals 0. So, what do you do with that? That's x squared plus x minus 6 equals 0. Where's this denominator equal to 0, right? Okay, so you got two values here, right? What do you guys know? What does this mean here for the two values of x? Which ones are, where's the vertical asymptotes? Anybody know? Well, it's at negative 3 and 2, but in the interval, so in other words, I get to throw this one out, right? So in other words, 2 is in the interval, right? 2 is in that interval. This is your in, it's meaning element of. So integrate this from what now? This is going to be the integral 0 to 2, 1 over, I'm going to put the x plus 3 version, x minus 2 factored version, plus 2 to 4, 1 over x plus 3, x minus 2 dx, right? Okay, you guys okay with that one? So the problematic discontinuity is at 2. So in other words, now we have a situation where if you said this is 0 to 2, 2 to 4. This is a right endpoint discontinuity. This is a left. All right, right, left. So then now you go, oh my God, there's going to be two integrals to do. So let's try to do the first one. And this, right, we got two of them to do now. Right, so what does this one become? Right, so I'm going to work on that one, that definition, and I'm going to redo this, sorry. A little bit of OCD, but let's put that back in blue. 0, bless you. X plus 3, x minus 2. Okay, so problematic is at 2. So this isn't be the limit. This is a right endpoint. T goes to 2 from the left. Is that right? 0 to t, 1. That's x plus 3, x minus 2 dx. So let's ask you guys here. What do you guys use here? Anybody know what you guys use? Partial fraction decomposition. Now, I'll just put a note here. Remember, 1 over x plus 3, x minus 2 becomes a over x plus 3 plus b over x minus 2. Okay? And I tell you, by using partial fraction decomposition, you get a is negative 1/5. You're going to get b is positive 1/5. Okay? So in general, when you integrate x plus 3, x minus 2 dx, so you guys know, that's going to be the integral of 1/5 x minus 2 minus 1/5 x plus 3 dx. So you guys know. And so you're going to end up with 1/5 natural log absolute value x minus 2 minus 1/5 natural log x plus 3. And really 1/5 natural log x minus 2 over x plus 3. Because you can use properties of logs there. So we have some properties of logs. And don't forget, this integral is really from 0 to what? 0 to t, yeah. Okay? Remember, 0 minus 2 is negative 2. 0 plus 3 is 3, but you're taking the absolute value of a negative 2/3, which is positive 2/3. Okay, so anyway, just so that you guys know. Now, what's the limit here, though? Limit as t goes to what? 2 from the left. So you're going to now have to take this limit now. And this is just going to be a constant. So limit of a difference is difference of the limits, right? But I'm just going to say, let's focus on this limit right here. Right? That's... Anyway, it's kind of bad to do that way. It's nicer to just say, let's look at the limit here. Well, all right, let's use properties of limits. Let's just stop. Stop with the nonsense. Stop trying to... Sometimes we do have to write, ladies and gentlemen. You know what I'm saying? Sometimes you just have to write it all down. Properties of limits, though. So I did the limit of a difference of a limit. Limit of a constant is a constant. Now I can get away with saying to you guys, hey, focus on this one, you know. Right? You guys know what I'm saying? Because you do have that constant on the right there. So we're going to have to kind of figure out what this limit is. Okay? So remember, this is going to be as t goes to 2 from the what? From the left. There's a couple of things I can do here. What do I want to say to you guys with this? A couple of things I can say and do here. As you go to 2 from the what? From what direction? We could do a couple of things, I think. I'm thinking of one thing. Okay, 2 from the, what direction? We're going to 2 from the left. So in other words, I don't know, what is, if t is going to be 1 point what? 99999. Here's what I want to really get at. Where does t minus 2 over t plus 3 go to? Do you guys know where this portion goes to? If I try to, let's use a different color. Where is this going to? That's my point. It's going to 0. Good job. How do you know it's going to 0? If you use this small value, right? Doesn't this numerator go to 0 and the denominator go to 5? 0 over 5 is 0. Good job. Now, what comes next? What does the natural log of t minus 2 over t plus 3 go to? You want to focus now on what curve? Yeah, natural log curve. What happens is you go to 0. Can you guys think of the natural log curve? Yeah, where does it go to? Are you sure? Let me get the natural log curve out. I don't know. I have no idea. Are you sure? Isn't this the natural log curve? Remember I said curves every whatever, blah, blah, blah. This is going where? Negative infinity. Is that right? You guys see what I mean? We're not going to 1. If you're going to 1, it'd be 0. Because this particular point is 1, 0, right? We're going to 0. So we know this portion goes to minus infinity. What's minus infinity minus a constant? It's negative infinity. Good job. All right, you guys okay with that one? Negative infinity diverges. Don't have to do the other one. No. That's my point again. Don't even do the other. So we know this one what? Diverges, right? Let's go back here. So this one here, let's put it big. This one diverges. You don't have to do the other one. Okay, if this one diverges, then the whole thing what? Diverges. Yeah, that's kind of like why I wanted to get to this one too, because it was like, yeah, that's, it, you know, sometimes like you say, oh, I had to do all this work for one integral, but be happy if you did all that work and it diverged. I mean, don't make it diverge, but, you know, when it doesn't, but it diverges, you go, oh, I don't have to do the other one now. It's only one integral. Yeah. Yeah, it's kind of an interesting kind of, like I said, it's a very interesting kind of thing. Anyway, it's going to come out to some of those. Should we take a break or should we try another one? Huh? You want a break? All right, we can take a break. Yeah, let's take a break here. All right, here we go. 15 minutes, there, break. All right, we'll be back. pancakes and bacon or something. I don't know. Is it too early for pancakes and bacon? Yeah, I'm. So if you want to know the secret, I guess who's, I know some of you guys at home there. I don't know, is it Oscar? I think Oscar, right? So if you're a baseball fan, I'll let you guys in on a little secret, okay? You baseball fans out there. I ran into Tim Hudson, and I ran into some Cincinnati Reds players. Tim Hudson was like a couple of years ago, I think, when he played with the Giants. And then Cincinnati Reds, I ran into some players there. Cincinnati Reds having breakfast in the Pasadena area, you know, very popular kind of Pasadena. Well, it's not very popular. It's popular, but it's not as popular as some others. It's kind of a hidden gem. I think the hotel where the visiting team stays at is close by. So, you know, they go and they have breakfast. They don't want to stay in the hotel necessarily. Get out, have some breakfast. So I run into players there. So if you guys want to know where that place is, you know, contact me and I'll let you know. And maybe you go have some breakfast when the Dodgers are playing at home and a visiting team comes in. Maybe you want to check out my theory, my hypothesis. But I think I'm right, you know. Yeah, I don't know if you guys notice. Have you guys eaten out lately? Something is not right. Maybe it's me as an old guy. But I've noticed, I mean, sometimes food, it could either be the cook, quality of ingredients. Maybe people are trying to save on costs, you know? And sometimes food doesn't taste as I'd say as rich as it used to. I'm talking pre-pandemic, you know. So the food here is okay, it could be good. It's like sometimes it's hit and miss. I mean, it's a popular place. I like the place, Martson's. I guess I'll tell you where it is. It's good, it's okay, but I'm kind of a, my daughter says you're a little picky. Kind of picky about some things, you know. Like if you have breakfast potatoes, it has to be good, in my opinion. Don't give me some bad potatoes for breakfast, you know. And not everybody can do it well. And if that comes back not so good, you know, or you get like the bacon ain't great and the sausage isn't good, you're like, what did I do? Why did I even do this? You know. So, you know, it's pretty good, but it's I don't know. Yeah, and if it's expensive too, then you're like, oh, it's like that's why In-N-Out is always so good because it's typically good and it's not expensive. You know. Yeah. But some places, like I said, you could go to a good breakfast place, and if it's not good, it's really disappointing. But it's okay, you know. And I don't eat as much as I used to. Ironically, it's kind of weird. If I order an omelet, right? You get an omelet, a good fancy omelet. Sometimes they give you like this big omelet. It's like I can only eat a third now. Where before I might eat the whole omelet. And I'm like, I'm only going to eat a little bit of this omelet. So I ordered the Texas chili omelet, you know. I ate all the Texas chili, but I left most of the omelet. Potatoes were okay, but it's all right. It's a pretty good place, though. I got to admit, it's pretty good. It is good. So yeah, if you guys, I think Oscar likes the Dodgers. If you want to go there, Oscar, take a look. That's going to be fun. Yeah, I told my family, I think when the Mets come in and Scherzer comes to town, maybe he'll show up. This is going to be one interesting kind of question here. So I'm going to give you guys some examples because, like I say, I kind of take them from the book and share with you guys how to go about this. Remember, your function is supposed to be continuous over the interval. For these questions, it's not. This is like from 0 to 2. So you'll have 2x minus 3 equals 0. Solve for x. Notice at 3 halves again. What's the deal? That's 1.5. That's going to be discontinuity again. Darn it, it's not even at an endpoint. So you go, okay. So it's discontinuous at 3/2. 3/2 is in that interval. So you go, okay, f, just to go to notate, is discontinuous. And x is 3/2. But you know, they have actually pretty good breakfast, pretty consistent. It's another Pasadena place. Gosh, what's that place? I go there all the time even. My wife always says, hey, let's go here. It's pretty good money too. It's not expensive. It's not an expensive place. It's probably why it's very popular. It's not expensive with a good breakfast. God, where's that place called? Where does Juan have it? Earth Cafe? No, that's expensive, Juan. Oh, forget it, man. That place is expensive, and you're not even going to... I don't know about you. I get the pot roast sandwich, and it's more bread than anything else, you know. And it's expensive. No, where's that? Pasadena breakfast. God, it's going to drive me crazy. I go there. You probably see me there. This is a good expense. Pasadena breakfast. I know where it is. It's adjacent to... how is it adjacent to? Yeah, I can... Russell's. Russell's in Pasadena. Yeah, there you go. I go to Russell's in Pasadena. That's a good price. But they have like $2 amounts. I don't know. I don't think so. It's pretty popular. 4.6 out of 5 stars. Yeah, you're gonna wait, but if you go, you got to get there really early for no wait. Like if you wake up early, get out there. You know, if you're gonna be there at a typical breakfast time, you're gonna wait. And that one's good. That's a good place. Earth Cafe, you're right, has good breakfast, but that's super expensive. IHOP, yeah. Marston's in Pasadena. That's the place, though. Marston's was where I run into baseball players. Yeah, I'm looking on online. And Crepes de Paris is good. I used to take my daughter there. Einstein Bagels. I hate to say it. I get the pizza bagel for breakfast. It's actually pretty good. Yeah. And then, you know, and then what did I eat? Where did I go in Pasadena? I ate this Mexican restaurant. It wasn't that good. Forget the name. Yeah, it was kind of expensive, but not. I don't know. It was all right. Anyway, here we go. So, in other words, this is discontinuous, not at an endpoint. So you're going to have to break it up at the endpoint. So hopefully, it's a divergent situation that you integrate once. So I'm gonna go back here. 0, 3/2, x minus 3 over 2x minus 3 plus 3/2 to 2. Yeah. Yeah, 1.5, 0 to, yeah, that's good. Mentally, I was like, yeah, 1.5, so it was there, yeah, between 0 and 2, so. Anyway, okay, this is going to be here. Remember, this is this interval, 0 to 3/2, that's the right endpoint, discontinuity. So you'll start with that one, you know. This one is a left endpoint discontinuity. You know, you can start with either, really. But I'll start with this one here. Now, this question here, be careful with because, you know, there's a couple of ways you can do this one. I'm going to share with you guys a nice trick that I do. Not a nice trick. This is, okay, you see this function here, right? They have the same powers, numerator and denominator, because if you separate this, right, you have a difference. So if you said, I'm gonna separate this integral as a difference, here's what I'm saying to you. You might be tempted to say this is x over 2x minus 3 dx minus the integral of 3 over 2x minus 3 dx. You might be tempted to do something like this and say, I want to, this one you can integrate easy, right? U sub. This one, not so easy. Can't do U sub with that one. I mean, you might be able to argue with it. I think it's going to be hairy. You might be able to do something. But I look at that and I go, not kind of sure. Here's what I'm going to say to you guys. Here's something that is very helpful. You see how the numerator and denominator have the same degree, highest power? You know what you can do? Divide. Okay? You might say, what do you mean divide? Yeah, when they have that same power, you can kind of simplify this a little bit. So, do you guys remember division? Right? You do x over 2x, the division algorithm from, this is actually beginning algebra. That's going to be 1/2. So, oh, that's a constant, 1/2. So then take the 1/2 and multiply it to the 2x minus 3. So you end up getting here x minus 3/2. Change your sign, right? And you get a minus 3/2 now. Okay? So you might say, what does this do for you? Well, you're taking x minus 3, 2x minus 3. The quotient is 1/2. This is minus 3/2 the remainder over the 2x minus 3. You're writing this as a mixed number or, yeah, here's your mixed number. So as you integrate now, notice what's nice. Not a lot nicer to integrate? Now you can integrate. That's kind of a little trick when you have the same degree. And I can say you can kind of kick that around. That's helped me out tremendously. So this is from 0 to 3/2. So here's what we're saying here. Integrate. 0, 3/2. 1/2 minus the 3/2 over 2x minus 3 dx. 1/2 integral 0 3/2 dx minus 3/2 integral 0 3/2 1 over 2x minus 3 dx. So let me double check. Did I make a mistake? No, I'm good. 3/2, right? However, here's what we didn't do. You guys know what we didn't do? This is kind of bad. Let's go back a bit. This is bad. We got too excited. Yeah, we didn't write it. We didn't use the definition. So let's take a step back. I seen that and I'm like, oh, I want to get started in integrating. So here's the problem. This is bad, right? Here's what I'm saying to you. This is by definition. Remember, by definition, this is the limit now. As t goes to 3/2 from the left, 0 to t, x minus 3, 2x minus 3 dx. You guys see what I'm saying? Got to use the definition. So, we know already what this will be. Okay, that integral is what we see right here. Integral of 1/2 0 to t dx minus 3/2 0 to t over 2x minus 3 dx. This is a 1/2 what? X. And then you're going to use u sub, right? So this is going to become minus 3/4 natural log absolute value 2x minus 3. 0 to t. So remember how I sometimes write that because it helps me. 1/2 t minus 3/4 natural log absolute value 2t minus 3 minus another parentheses 1/2 times 0 minus 3/4 natural log absolute value 2 times 0 minus 3. Okay, so if you have every detail there, 1/2 t minus 3/4 natural log absolute value 2t minus 3. This part is 0. And you're going to have here a negative 3, right? Absolute value, though. So this is going to be a minus now, or a plus, because you distribute the sign. 3/4 natural log of 3. Because the absolute value of negative 3 in there is positive 3. And this limit is t going to 3/2 from the... All right, I'll scroll down there. T goes to 3/2 from the left. All right, so we're going to have to wonder about this one here. You say, what happens with this one here? So I actually have, if I use properties of limits, well, let's use properties of limits, right? Isn't this going to be, remember, t is going to what? So if I highlight, t goes to 3/2 from the left. So there's t there, t here, right? So by properties limits, I could do the limit. This is 1/2 times 3/2, 3/4 minus 3/4. Limit. T goes to 3/2 from the left. Natural log, absolute value 2t minus 3. And then this is limit of a constant, so it's just going to be your constant. Okay, you guys okay with that one? Right? You guys okay with that? So what I'm really saying is we're going to have to focus right in here in the limit. Everything else is a constant. Right? You guys okay with that? So here's the logic. As t goes to 3/2 from the left, right? 2t minus 3. Where does that go to? That go to 0? You guys know what I'm talking about? Now, that means the absolute value of 2t minus 3, because the absolute value is continuous everywhere. So you're looking at limits of a continuous everywhere. That means the absolute value of 2t minus 3 also goes to what? 0. And then what does the natural log go to? We already seen that. That goes to minus what? Infinity. Okay? So minus infinity plus these constants really mean what? The whole thing is minus what? Infinity. Okay? So this is a divergent situation. And like I said, this integral diverges. And that means you have a wonderful, wonderful thing. We don't have to do the other integral. This one diverges. And so that's, that's a nice thing, because you go, okay, good. That's another way of saying divergence here, so we know about that, okay? Anyway. And then I see a problem here I like in my notes. Do I like this one? There's a few interesting questions. Let's look at something like this one. To infinity dx over x squared plus 2x minus 3. And I'll put 1 over dx. What do we know about this? All right, this is x. If we factor this, you guys know what's happening with that denominator, right? Because what I'm concerned with is this function continuous from 2 to infinity. This might be you say, what's going on here with this one? This problem here, let's factor it first of all. I don't know, 3 plus 3 and minus 1. Is that true? So we set this equal to 0 here. And what that means, yeah, x is negative 3 here, and then x is positive 1. Is that right? So we go, oh, what's the deal? Our interval here is from 2 to infinity. So, so this is the first type. This is an infinite interval. So we're safe. Is that true? You guys know what I'm talking about? Did we do this one the other day? No? No? Okay. All right. Well, then this is not, you have vertical asymptotes where x is negative 3 and x is 1. There's your vertical asymptotes, but it's outside the interval. Right? So it's continuous over the interval. You might say, what happens if it's not? Well, I mean, I'm trying to remember if there might be like one question like that in the book. It's like at the end. I don't know if I assigned it. But, anyway, you would use both definitions. I won't. Should I show you guys what I'm talking about? Just give you guys a note. Just a what if. Something like this, I don't think they did. If they changed that from 0, right? X squared plus 2x minus 3. So now you have a combination. You have a vertical asymptote at 1. All right, you guys see what I'm saying? See this? It's not what they gave you. So if they change that interval on you, what do you do if your vertical asymptote happens at x is 1? Now there's a discontinuity over an interval. Now you have this discontinuity over the interval. And you might say, can I split it up? Yeah, you split it up from 0 to 1. Remember, over the discontinuity. Plus 1 to what? Infinity over the discontinuity. Right? But then here, so let me emphasize, 1, 1. But over here, you also have what? The infinity. So they got two things going on. Okay, just to kind of show you guys in general how you would do this. There might be one question in the book, but I don't think I assigned it, but I can show you how you would do it. Okay, so you say, okay, I split this up on the discontinuity at 1, but I know and I have my first integral. This is what I can integrate this one by using my definition. But then you have this second integral, and it has two things going on, right? You have an infinite discontinuity at 1, and you have another limit. That's an infinite interval. Infinite discontinuity and infinite interval. Let's write that down. So you might say, how would you handle that? Well, split it up. Give me a number that's bigger than 1. Any number. 3. Okay. Integrate from 1 to 3. Oops, sorry. So in this now, the point I'm making is your green integral is now 2. And that's how you would split this one up. Just pick some number, any number between 1 and infinity, integrate there, and then add the second integral. So what you would need is convergence in all three. Okay, you understand what I'm saying? You'd have to have convergence for all three. The second you have divergence, then you'd have a problem. And then worse yet, it's a partial fraction decomposition, So that one's going to be a fun one. Anyway, go back to the original. So let me write that one down. So we're going to integrate the original one here. Oh, I should have copied it. Let's copy it. So just kind of give you that nice remark. I don't think I assigned anything like that, but anyway. All right, so that's going to be the limit. T goes to infinity, so you're back where we full circle. 1 over x plus 3, x minus 1 dx. So this is going to depend on what this integral is by partial fraction decomposition. Okay? And there, t is at infinity. So to let you guys know what that really is, 2 to t, partial fraction decomposition, it's going to be the following. So 1/4 t 1 over x minus 1 dx minus 1/4 1 over x plus 3 dx 2 to t. It's really 1/4 natural log absolute value x minus 1 over x minus 3 2 to t, which is 1/4 natural log t minus 1 t plus 3 minus 1/4 natural log 2 minus 1 2 plus 3 1/4 natural log absolute value t minus 1 t plus 3 minus 1/4. That's natural log of 1/5. I don't know why that sounds familiar, like we did it already. I don't know, but if you guys say we didn't do it, we didn't do it. And then the limit, what's the limit now? T goes to what? Infinity. So limit t goes to infinity, 1/4 natural log t minus 1. I'm going to use properties again, and here's what we get. So this is where that limit's going to be, right in here. All right, let me ask you guys a question. How did you find that limit? Anybody know? Do you guys know? How would you get that limit? You want to? Can I share with you guys again that little trick? Just share with you guys something. 1 t plus 3 subtract -4. So that's going to be 1 minus 4 over t plus 3, right in here. Okay? You see what I'm saying? If you do the division, this is something that's really nice. So, as t gets big, 1 minus 4 over t plus 3, where does this go to? That goes to 1. So that means the natural log of the absolute value, well, that means the absolute value goes to 1. To give you every detail, goes to absolute value 1, which is 1, right? Which means the natural log of the absolute value, 1 minus 4 over t plus 3, goes to the natural log of 1, which equals what? 0. In other words, this goes where? To 0. And this means the answer is minus 1/4, which is really 1/4 natural log of 5 if I use properties of limits. This is a nice finite number. This is convergence. So we go, this thing converges. You could put symbolically less than infinity. You got convergence. Anyway. All right. So what do you guys think? We came full circle. I didn't give you another one of those kind of questions. I think Juan had a question on an example, and I should have kind of talked about it instead of this one. This one looks familiar. But I wanted to share with you guys a little bit of that detail, how that one would look if they just change that interval. So a lot of these intervals are very specially chosen for you. Okay? Especially chosen, so it's, believe it or not, if you just said, even if you said, I want to integrate this whole thing, I mean, I remember as a student, personally, if they had to integrate this from the whole real number line. Okay, this has probably about 5 or, I don't know. I think it's 2, 4. This has 6 integrals. Maybe more, 8 integrals. Now, am I going to give you that? No. Waste 8 integrals, I mean, hopefully the first one diverges. But this, if you go over the whole real number line and you start mixing your 2 types together, you say, what are the types? Infinite intervals and infinite discontinuities. That's a real kicker-upper. You can really kick things up that way. Anyway, all right. All righty. So here's the deal, right? What did I do for you guys, right? I put your homework in, but this is what we wanted to go over, these definitions. And I did give you case 3. You just add the, I gave you that earlier today, case number 3, right? That's what we started with the first example. So here's kind of what we call the notes maybe, or just the guideline for what we were doing. And maybe we should scroll out. And, okay. So where are we at there? All right. So I did put that homework. Some of you guys already started to work on it. Homework 3. Let's put that. Wait a minute. You guys aren't 227. You're 262. So, yeah. So it's already in homework 3. I'm going to kind of even say, if you can, start reading on the next section. Chapter what? 9. So if you guys want to start reading the next section, that would also be good. Chapter 9. Arc length and surface area. Yeah. You guys can start reading that. Okay, so you guys want to start reading chapter 9, 9.1, 9.2. And ladies and gentlemen, print your name in the comments section, and we'll see you guys when. We'll see you guys on when I see you. All right? Whatever that is. I don't even know what day or time it is. So take care.